Here's our next example of how to deal with projectile motion. Here is again a classical example. Here we have a projectile being shot out at some unknown velocity. We're supposed to find out what that velocity is at an angle of 30 degrees, 100 meters away from a wall that's 10 meters high. And we want that projectile to clear the wall. So what should be the minimum velocity at which this projectile is shot out so that it will make it over that wall? So first of all, since it's shot at an angle, let's first begin with finding the x and y components of that initial velocity. So v initial is going to be equal to v, in the x direction is going to be equal to v initial times the cosine of theta, which of course is 30 degrees. And here v initial in the y direction is going to be equal to v initial times the sine of 30 degrees. And then the next step, we're going to find time in the air. Now we're going to have one slight problem here, so let me show you why that is. So typically we'd say time in the air, and of course we use the equation y equals y sub naught plus v sub naught in the y direction times time plus 1/2 gt squared. Notice that the final height has to be at least 10 meters, so we'll make that a 10. The initial height will start from the ground at 0, plus the initial velocity in the y direction, which is of course v initial times the sine. We'll just write theta for now. We'll plug in the 30 degrees later. And then this would become minus 4.9 t squared. Notice we cannot solve for t here because we don't know what the initial velocity is. But here's the trick. Since we know that the time in the air in the y direction must equal the time in the air for the x direction, we can also use a second equation. So this would be for the y direction. And in the x direction, time in the air. For the x direction, it would look something like x is equal to v initial in the x direction times time. And of course, time appears there as well. So let's go ahead and plug in what we know here. We know that x is going to be 100 meters. And v initial in the x direction, that's going to be v initial times the cosine of theta times the time t. If we now solve this equation for time and plug it into our equation right here, and oh, notice that I forgot my t here. I can't do that. Got to have a t in there as well. If I then plug it into here and here, then I can eliminate time. And then I only have an equation with v initial as its only variable. And I can simply solve for v initial. So kind of in a roundabout way, by using time in the air for both the y and the x direction, I can actually eliminate the t. And I can then go ahead and solve for the only variable I don't know that's left, which is v initial. So here we can say that t is equal to 100 divided by v initial times the cosine of theta, and we'll plug that back in here. So that gives us 10 is equal to v initial times the sine of theta. And instead of t, I'm going to write this right here. So times 100 divided by v initial times the cosine of theta. And then minus 4.9 times t squared, which is this quantity, 100 divided by v initial times the cosine of theta, and the whole thing squared. So now I have to simplify this. Notice that v initial and v initial cancel out. The sine and the cosine, well, the sine divided by cosine is the tangent of theta. So this becomes 10 is equal to 100 times the tangent of theta, which is of course 30 degrees in this case, minus 4.9 times 100 divided by v initial times the cosine of 30 degrees, and square that. So I have 30, take the tangent of that, which is 0.577, times 100. All right, so now I have 10 is equal to 57.7 minus, now I'm going to multiply all this out and divide it by v squared, because of course v is squared here as well. So 100 divided by the cosine of 30, we square that, we multiply times 4.9. Okay, so this is equal to 65,333 divided by v sub naught squared. All right, now that looks a little bit better, because now I'm simplifying this. I have v sub naught that I'm solving for. So let's move this across to the other side. So now, and I need some room, so I'm going to move it over here. Move the 57.7 over, becomes minus 57.7 plus 10, which is minus 47.7. equals a minus 65,333 divided by v sub naught squared. The next step is to move this over here and this down there. So we have v sub naught squared is equal to minus 65,333 divided by minus 47.7. Notice here that the negatives will cancel out. So divide this by 47.7. And then, of course, v sub naught is equal to the square root of that. And then take the square root. And I get 37. So v sub naught equals 37 meters per second. Okay, notice that, of course, I left off the units to make all this a lot cleaner. This would look really ugly when you keep the units in there. But eventually, the answer is here. So even though we started out by solving for time in the air, and we realized that we couldn't do that because time was not known and v initial was not known, if we then solve it simultaneously by doing the y in the x direction at the same time, solve the equation in the x direction for time, plug that into the t and t squared here for the equation for the y direction, and then you're left with only one unknown, v sub naught, solve for v sub naught, and get the answer. And that's how you do a problem like that, where you're trying to clear a certain height at a distance with a projectile.